Hello, and welcome to Gennaro Salas's function of love. Right here is the graph of our function. As you can see, it is a rational function with a vertical asymptote and a horizontal asymptote, and it includes one discontinuity, which is a hole. We will get into this a little later. First, we're going to break down r of x. Here, r of x is equal to x squared plus 2x minus 3 over x squared minus 1. If we break that down a little further, we find out that it is x minus 1 times x plus 3 over x minus 1 times x plus 1. Because the numerator and the denominator both have x minus 1, we cross that out and find out that there will be a hole at x equals 1. Our numerator f of x has roots at x equals 1 and x equals 3, and our denominator g of x will have roots at x equals 1 and x equals negative 1. If we continue further, we will see that to find the vertical asymptote, we need to set the denominator to 0. When we do that, we get x equals negative 1 as our vertical asymptote, and to find the horizontal asymptote, since the degrees for the numerator and denominator are the same, we will divide each one and get y equals 1 for a horizontal asymptote. Now going back to our graph, we see that we have the horizontal asymptote at y equals 1, and so as the function approaches negative infinity, the limit is going to equal 1, and as the function approaches positive infinity, the limit will also be 1. And if we zoom in over here a little bubble, we see that there is a hole at x equals 1, and because of that, the value is undefined. However, the limit will still exist, and the limit will be 2. Now let's find the first and second derivative. So because this is crossed out, we will only be taking into consideration x plus 3 over x plus 1. We know using the rule that u prime of v minus u times v prime over v squared is going to equal r prime of x, and if we plug that in, we will get negative 2 over x plus 1 squared as our first derivative, and if we continue using that rule for our second derivative, we will get 4 over x plus 1 cubed. Now, when we analyze our graph, we are going to use the numerator, and we get a y-intercept at 0, 3, and a x-intercept at k root at negative 3, 0. When we go into the first derivative to find all critical points, we realize that the numerator is a constant, and because of this, it will never reach 0. So when x equals negative 1, the function is undefined, but because the vertical asymptote exists at x equals negative 1, the point will not exist, and there are no critical points. Additionally, because the derivative never equals 0, there are no local extrema. When we find our increasing and decreasing intervals, we see that the numerator is a constant of our first derivative. And because of that, we know that x does not equal negative 1 because of the vertical asymptote, but all values that take of x will make it negative, so we know that the function will decrease in the interval negative infinity to negative 1 and negative 1 to infinity. To find concavity, there are two intervals that we need to consider. Due to the vertical asymptote, we are only considering negative infinity to negative 1 and negative 1 to infinity. So to test on the interval of negative infinity to negative 1, we're going to use a second derivative, and we're going to use negative 3 for c, getting negative 1/2. Since r prime of x is 0 and the second derivative is less than 0, when we know r of x is concave down on the interval negative infinity to negative 1. Now to test on negative 1 and infinity, we were going to use 1, again plugging that into the second derivative and getting 1/2. Now because this time the second derivative is greater than 0, we know that f of x is concave up on the interval negative 1 to infinity. Now for the mean value theorem, we are going to be using r of x on the interval of 2, 4. A will be 2 and b will be 4. So we know the function is continuous on the interval. Yes, there is a hole at x equals 1, but that is not included on this interval, so we will be fine. And secondly, we need to make sure that it is differentiable. Of course, we already found the first derivative earlier, so we know that the function is differentiable. When we continue, we know we need to find f prime of c equals f of b minus f of a over b minus a. Now, to solve this, we got negative 4 over 30, which simplifies to negative 2 over 15. Now we sub in c for x, and we'll get negative 2 over c plus 1 squared equals negative 2 over 15, cross multiplying to continue, and we will end up getting c equals negative 1 plus the square root of 15, and c equals negative 1 minus the square root of 15. And when we solve that, we get c equals 2.87, and c equals negative 4.87. Now negative 4.87 is not included on our interval, so in this case, the answer will be c equals negative 1 plus square root of 15. If we zoom in on the interval, 2, 4, again, continuous and differentiable, we know that c will be about right here. For the intermediate value theorem, we want to use it to prove that our root exists. So we know on the interval negative 5, negative 2, the function is continuous, and the intermediate value theorem tells us that a function is continuous on an interval ab must take every value between the endpoints. And since negative 3 is in between this interval, we know that the function must take every point in between, and negative 3 falls under that category, so it is a point that exists. Again, we see over here, from negative 5 to negative 2, it's continuous, negative 3 is in between there, so the intermediate value theorem proves its existence. Now, the extreme value theorem, and remember that tells us that a function continuous on a, b must have an absolute minimum and an absolute maximum on that interval. So if we're going to use the interval negative 4, negative 2 with our function r of x, we already found out that there are no critical points on the interval, so the only thing we'll be taking into consideration are endpoints a and b, which we'll get 1/3 for negative 4 and negative 1 for negative 2. So there's going to be an absolute maximum at x equals negative 4 and an absolute minimum at x equals negative 2. Going further, we can see over here that our absolute maximum will be over here at -4, and down here we'll have our absolute minimum at -2. Now, to find the tangent line, we know we're going to need, obviously, the function. We have our point, which we're going to use our root, -3, 0, and to get the slope, we know we have to find our first derivative, which we found earlier, -2 over x plus 1 squared, and if we plug in -3, we'll get -1/2 of our slope. We plug it into the equation, and we'll get y equals -1/2 x minus 3 over 2 for the equation of the tangent line. For the normal line, we know that the slope is just the opposite reciprocal of the slope of the tangent line, so we'll get a slope of 2 for the normal line, and the normal line will equal y equals 2x plus 6. When we graph it over here, we can see our function. Our point is -3, 0. This line over here being the tangent line, and this line over here will be our normal line. And that's it. Thank you.